Yes, but we still have 30 seconds by my clock.
I forget how good you are, David, at the literal interpretation of the definitions.
All right. Okay, so it seems to be time. Are you ready, Dan?
Sure. Yeah, can you hear me?
Yeah, let me just start the recording. Okay, welcome everybody. We have today Daniel Halpern-Leistner from Cornell, and he's going to talk about dimensional GAT.
Okay, thank you very much for the invitation. I was hearing a little bit of a lag when Ron was speaking, so I don't know, let me know if I start to break up.
Sound fine.
Okay, good, okay. Okay, so yeah, so I'm gonna tell you about joint work in progress with Eduardo Gonzalez and Andres Fernandez Herrero. So there's been aspects of this project have been kicking around for a while, but we've made a lot of nice progress recently. So and it's nearly complete, so it seems like an appropriate time to give a talk on it. For the whole talk, just for simplicity.
Now there's a lag.
There's a lag. Okay.
Ron, I think the lag may be you. I have no lag from Dan.
Okay. Okay, great.
All right, I'll just mute myself then.
Okay. So for the whole talk, we're going to work with the Riemann surface over C. Just for simplicity, I mean, in actuality, it's more of like a sort of EGA style thing. It works for smooth families of curves, but there's no, it's clearer to think about it this way. And we're going to consider the algebraic stack just to warm up. The algebraic stack of vector bundles of rank n on C. And this is what's called a mapping stack in algebraic geometry. This is the stack of maps from C to BGLN. And basically the way that you think about this is a functor of points perspective. So this stack is the thing such that a map to it is equal to a rank n vector bundle. So I guess the groupoid of maps from T to bun n is the same as the groupoid of rank n vector bundles, holomorphic vector bundles on C times T. This is a functor of points perspective. And now, you know, in algebraic geometry, people are very interested in you know, parameter spaces of things, moduli spaces, and just more generally interested in sort of classification problems. And in a kind of tautological way, this algebraic stack is a solution to the classification problem. So there's some nice properties of this algebraic stack. I mean, there's nice properties of this functor of points, which are summarized by saying that it's an algebraic stack. Yeah, that's right. If people have questions, go ahead and interrupt. And I'm not going to get into what that means, but in some sense, this is a tautological, this is a geometric object, and there's a rich geometric theory of how to work with sheaves on algebraic stacks, and talk about, you know, cohomology and constructible sheaves and all kinds of stuff. And so you can think of this as a geometric object in its own right, a solution of the moduli problem, a solution of this classification problem. But in this example, this classical example, there's much more that's possible. And so the real solution, I would argue, is not just the algebraic stack. So solution to the classification problem is actually a certain kind of special stratification of this moduli problem. So it's a special stratification. For me, a moduli problem is synonymous with algebraic stack. And so I just want to recall what that is and try to explain a little bit. So, I mean, the issue with just thinking about the stack of bundles on the curve as the final geometric object is that, first of all, it's unbounded. So it tends to, there's no finite type variety that gives you a universal family that hits every possible isomorphism class of vector bundle on the curve, even if you fix the rank and degree. So that's like the first issue, is that it's unbounded. And the other issue is that it's highly non-separated. And so you can have bundles degenerating to other bundles in many, many, many different sort of ways. So the story I'm about to tell you is a way of kind of taming this kind of these two issues. And again, this is just very classical, but I just want to review because it's not too far away from what I'd like to tell you about today. So basically, the story is you have a semistable locus. So that's basically a vector bundle is semistable if there's no subbundle. There's not, it is a subbundle of larger slope. And I'll explain what that means visually in a second. But the point is that this condition, this defines an open substack. And this open substack admits a projective good moduli space. I mean, technically, in order to get something bounded, you have to fix the degree as well. But once you fix the rank and degree, you get these much more mild algebraic stacks that actually have good moduli spaces. And you can even say that the moduli points of the moduli space parameterize bundles up to a very mild equivalence relation known as S equivalence. Oops. Can you hear that background noise?
It's very mild.
Very mild. Okay, I'll leave it alone. I could close the window, but it's more comfortable. Okay, so in some sense, the semistable locus is much nicer to work with, but it doesn't actually, I wouldn't call that a solution of the classification problem because you've cut out almost all bundles. You've cut yourself down to a bounded substack, but as I said before, there's, the moduli problem is sort of highly infinite. So, so to complete this picture, it's use the Harder-Narasimhan theory. So the theorem is that this is the Harder-Narasimhan theorem. It says that every unstable bundle admits a unique convex filtration. I'll explain. These graded pieces are semi-stable. Okay, so let me give a visual explanation for semi-stability just to and what the Harder-Narasimhan theorem is saying. So you can imagine a vector bundle has under this Riemann surface has two characteristic classes. It has its rank and its degree. And so you can imagine if you plot where the rank and degree is, if you start with the vector bundle E, so it has some point in this rank and degree plane. And the idea is that E is semi-stable if and only if every subbundle, semi-stability means every subbundle has to sit below or on this line. That's what semi-stability means for if I have an E prime inside of E. If you have a single subbundle that sits above the line, that's destabilizing. And what the Harder-Narasimhan theorem says is that there's a sort of, if now what I mean by convex filtration is if you take, let's say in this example, I call E, I just say E is E naught, and just for the sake of having something, oops, sorry. For the sake of having something visual, let me. Sorry, I'm having a little. Issue with my stylus here. So this is E1 and this is E2. And so by convex filtration, I just mean it looks like this. It lies above the line segment from the origin to E, and the slopes are literally the slopes of the line segment. So the slopes of the graded pieces are the slopes of those line segments. And I'll call this resulting polytope alpha. So alpha is what I call the polytope. Okay. And so it's kind of a remarkable theorem, and I'll explain it even more. It's even more remarkable when you sort of reformulate it slightly. But finally, if you add Schatz's name, you have that's what I would call the complete classification, the complete solution of this classification problem. Basically, that says that, Bun N of C, this algebraic, so it is an algebraic stack, and furthermore, it has a stratification of this kind. So there's a semi-stable locus, Bun N semi-stable union, and then a union over alpha, where the alpha here is the same as the alpha. Alpha indexes Harder-Narasimhan polytopes. And the strata are the loci of bundles with Harder-Narasimhan filtration of shape alpha. And this is a stratification by locally closed substacks. And not only that, but these strata themselves have a kind of structure. The filtration is also, because of the uniqueness part of the Harder-Narasimhan theorem, there really is a unique filtration for each of these bundles. And so each of these strata kind of projects, by taking associated graded, onto what I would call the center of the strata, which is just a product. So it's, Bun R1 D1 semistable times dot 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 bun RP DP semistable. So these unstable strata kind of fiber over, and in fact sort of deformation retract onto their centers, which is just remembering the associated graded pieces of the Harder-Narasimhan filtration. And the reason why that's interesting is because the associated graded pieces of the Harder-Narasimhan filtration, by definition, they're semistable. And so you can think of this as just also classified. This is also classified by a point in an algebraic stack that has a good moduli space. So this thing here has a good moduli space, has projective good moduli space. Good moduli space is a technical term, by the way, but it's a generalization to the language of stacks of basically what is the geometric invariant theory quotient. So in GIT, the quotient stack of the semistable locus by the group has a good moduli space, which is the classical GIT quotient. So this is so basically it's saying that if you want to classify a vector bundle, either it's semistable, in which case it's given by a point on some projective moduli space, or it's given, or it has a canonical filtration and there's a point on some other moduli space parameterizing the associated grade of the Harder-Narasimhan filtration, and the bundle is recovered from some extension data between those associated graded pieces. So in that sense, this is like a formula for solving the classification problem. And the goal of this circle of ideas that I'm going to tell you about is basically to discover the structure on other moduli stacks. So in this sense, it's part of a very, a sort of broad project that I've been working on for a few years. And, there have been other interesting, like KLT Fano varieties, and there's been constructed a stratification of this kind, and using some of this machinery. And but I'm going to tell you today about an example that's maybe of a lot of interest in enumerative geometry. So this is, I would say, my overall goal is to discover the structure, but I'm going to explain a specific application and hopefully motivate why, a way in which the structure is very useful. So are there any questions on the picture that I'm trying to generalize?
No reason you don't want to include the first stratum as just one of the alphas?
No, there's no reason. Yeah, you can think of semistable things as having a trivial Harder-Narasimhan filtration, like a one-step Harder-Narasimhan filtration. Yeah, I don't think. Yeah. Okay. Okay, so what I'm going to tell you about is the moduli of gauged maps. So basically, still working over C just because it's easier to think about. So let G be a reductive group. And again, for simplicity, let X be a linear representation. And so basically what we're going to study is an algebraic geometric model of the gauged linear sigma model. And so the stack we consider is the stack called MCG of X. And it's a mapping stack from the curve C to X mod G, the quotient stack. And basically it parameterizes a G bundle P over the curve C and a section of the associated vector bundle so to the linear representation X, you have this associated, you have an associated vector bundle, and you take a section. And you can think of this as a gauged map from C to X with gauge group G. So I mean, many things that people think about. I mean, so example could be a vector bundle plus an endomorphism. That's a nice example to keep in mind. Or it could be a vector bundle plus a section of wedge 2E. I mean, there's really all kinds of things. I mean, this example, you can also do Higgs bundles fits into here. So that's twisted by the canonical bundle, but there's a way to formulate that using basically this also a mapping stack. Right. So there are many kind of examples where this sort of stuff shows up. It's basically a G bundle along with some extra structure. And the motivation, though, is that is the following. So on this stack, there's a family of stability conditions depending on a real number delta. And the point is that for large delta, the enumerative invariance, well, let me just say it this way, that if you integrate tautological classes, on the moduli of semi-stable gauged maps, so there's delta semi-stability, is related by wall crossing to the Gromov-Witten invariance. To the Gromov-Witten invariance of the GIT quotient. So I'm imagining you have some GIT parameter chosen, and that allows you to formulate this notion of semi-stability. And then when if delta is very, very large, then eventually the notion of semi-stability stabilizes and you get a moduli space. And there is a theory of wall crossing that relates those to the Gromov-Witten invariance. So this is meant to be a way of getting at a computationally feasible way of getting at the Gromov-Witten invariance of GIT quotients. I mean, yeah. I mean, the Gromov-Witten invariants of the GIT quotient are nice because they don't actually make any reference to this particular global quotient description of the GIT quotient. Those are intrinsic to the semi-stable locus. But when you have a particular orbifold or manifold that you can write as a GIT quotient this way, then this would give you a method of computing it from something which arguably is simpler to compute, which are these integrals over the moduli of gauged map. So that's what I'm about to explain. So I'm going to focus on K-theory. The application of this project is K-theory. So So these are the integrals. So the K-theoretic integral is the index. So it's the integral over this semi-stable locus of some tautological class. I mean, so the formula won't help to understand it. So either you've been, if you're familiar with the numerative geometry stuff, then you can imagine your favorite tautological class in there. And the point is that this is, in K theory, the integral is the Euler characteristic. For this tautological class, just using the algebraic or the coherent cohomology. So there's a strategy for computing these. Yeah, and by the work of Woodward and Gonzalez, there's wall crossing formulas, as I mentioned, that relates these to K-theoretic Gromov-Witten invariants of the GIT quotient when delta is very large. And the strategy is a two-step strategy. So first of all, so you have a forgetful map. So this was a G bundle with a section. You have a forgetful map which just forgets the section. Forgets the section, forgets the map, basically, just the G bundle. This is affine, and P lower star of the structure sheaf has an explicit computation. So there's an explicit computation in K theory. And the upshot is that you can rewrite the integral over MCG of X without a stability condition. So the map, that in step one, there's no stability condition. You just have this huge monstrous stack, this enormous thing. And I write, if I take, there's a projection formula in K theory that says if I take the pullback of a tautological class on bun G to this stack of all gauge maps, and I integrate that tautological class, that's the same thing as integrating just over bun G of this P star of O, which I'm saying there's a sort of explicit formula for it as a symmetric power of a perfect complex tensor the tautological class. And the claim is that this object, there are known formulas. So the Telemann-Woodward formula gives explicit. And this is, it's a sort of, it's kind of like a Verlinde formula thing. There's a, it's a sum over solutions of some deformed Bethe-Ansatz equation, and so it's a, and there probably are deep reasons for that. But I'm not going to speculate in front of a group of physicists. I'm happy to speculate when I'm just talking to mathematicians, but I'm not going to speculate what the deep reasons in front of the physicists. But in any event, there's like literally a very explicit formula for this thing, and especially it's nice at not just considering a single tautological class, but certain generating functions of these tautological classes. But that's step one. The point is that also there's a little fib here, which is that the Euler characteristic is a priori not defined over MCG of X the whole stack. You have to argue why the cohomology groups are actually finite dimensional, and also bounded in order for that to be well defined. So, but if you just say, if you just go with the flow for a minute, so the second step of this strategy is a virtual non-abelian localization. So this is a K-theoretic there's a K-theoretic virtual non-abelian localization. So it says that the index over, now when I put the semi-stability condition in, this is equal to the index over the whole stack. Sorry, I've rewritten this already. So and then plus correction terms from the unstable locus. And really what you want is, so the non-abelian localization formula, this applies. The point is that this applies to a stack. It has to have a certain nice deformation theory, but it applies to a stack with a theta stratification. And I'm going to tell you what I mean by this, but this is the generalization of the HN filtration of Bun-G. Sorry, HN stratification.
Sorry, could you remind me why this is called a localization? It looks more like a statement of motivicness than restricting to some fixed locus.
Well, yeah, so the reason why it is most of the time the localization formula, you can recover the usual localization formula when the semi-stable locus is empty. So the localization part comes in the correction term. So so if you have like a I mean, it's related to a motivic decomposition, but like if you have X with a C star action, so if you choose a stratification that's sort of exhaustive, so if you take I'm drawing the fixed loci for the C star action and then a bunch of ascending manifolds. What this formula says is that the integral over X mod C star of something is equal to the integral over the semi-stable locus mod C star of something. But the semi-stable locus is the complement of the strata. So this is empty. Plus a sum, and the correction terms in this case would be the integrals over the centers. So let me call it like the fixed loci Z1, Z2, Z3. So it would be the sum over Zi mod C star of the 1 over the Euler class of the normal bundle. Times this thing restricted to Zi.
Gotcha. Thank you.
Yeah, so that's the more familiar. And but in order to make sense of this, you have to say, what do you mean by 1 over the Euler class of the normal bundle? And there's more words that you have to say effectively. But there's a class in a sort of completed version of K theory where that 1 over the Euler, that makes sense to say that it's 1 over the Euler class of the normal bundle. Yeah. So. I mean, in this case, we're using it somewhat differently because we're sort of interested in the semi-stable locus, and we're interested in removing. So yeah, I should say that the main application here of this I should say in progress, because this part of the paper is still a little bit of a mess, but the more but the main application is that for tautological for classes on Bun G, and if you take the point is that the correction terms vanish. So if you tensor with a line bundle with a sufficiently high level. So if you take the index over MCG of X delta semistable of whatever your tautological line bundle was, tensor L is given by the Telemann-Woodward formula. If L has sufficiently positive level. So I'm not going to define that. It's something that comes from, from Berlinda formula stuff. But basically you take these levels these line bundles on the stack that behave like they're like positive line bundles. And if you tensor with a sufficiently positive one, then the correction terms coming from the unstable strata all vanish for sort of a priori. They vanish for like a weight reason. You look at the integral and you're integrating something that has negative weight with respect to a GM action, and so the invariant cohomology has to vanish, and you're left with a very explicit formula for those gauge Gromov-Witten invariants. So that's the main application of the story. But to get there, all of this required that you have a stratification of this of the stack of gauge maps, of which this is the open semi-stable piece. And it's implicitly there in 1, 2, because, I mean, there are other ways, but, you want to show that those cohomology groups are finite so that the index is even well defined. So the stratification shows up there as well, in some sense. Yeah, so that's the main application of this idea. That's why you want something analogous to a Harder-Narasimhan stratification for these moduli of gauged maps. And so I'm going to tell you a little bit about how we prove that and what that really means. So this is all motivation. So are there any questions about this before I move on to a little bit telling you what I really mean by a stratification of this kind and how we know that, how we prove this theorem? Okay, so I'll tell you now a little bit about theta stratifications. And this just again is supposed to be a general notion of which the Harder-Narasimhan stratification of vector bundles on the curve is an example. Other examples are the stratification of the unstable locus in geometric invariant theory. And so it's called theta because the controlling object, or the key object, is this little stack that I like to call theta. Theta is A1 mod GM. And this is, and pictorially, kind of A1 mod GM has a single point with a GM fixed action in the center, and then another point 1 that kind of spins around it. So that's why I call it theta. It kind of looks like theta. And a filtration in a general stack is defined to be a map f from theta to x. So you think of this as a filtration. F of 1 is the underlying point of the underlying object, and f of 0. This, like I said, there's basically two points in this stack. There's 0 and there's every other point, which is equivalent of the GM action. So f of 0, though, that object has a GM action, and this is the associated gradient point. And the key in our example maps, so maps from theta to MC G of X are the same thing as sort of Z-weighted let me just actually, for simplicity, let me say that G, say G is GLN. So then it's just a Z-weighted filtered vector bundle. So and then such that, well, part of the data of this MCG of X, it's a vector bundle along with a section of some associated bundle. And so I want this filtration to be compatible. So I'll just say that is compatible with the additional data. For the E, which is the colimit, the union. So you think of this as a filtration for W. As W gets smaller and smaller and smaller, eventually this stabilizes. So maybe it's clearer to say E is EW for W much less than 0, and X is a representation of GLN. So whatever X is tells you what the sort of additional data is, and it's a section of some associated bundle for this vector bundle. So in our example, if you have E with an endomorphism, this is saying that the endomorphism has to respect the filtration. So it's not just filtrations of it's not just Z-weighted filtrations of the vector bundle. It's Z1 of the weighted filtrations of the vector bundle that respect the filtration. And you can there's a for any kind of sort of standard representation of GLN. You could try to give a case-by-case interpretation of what this is, but there's always just some compatibility that you have with this additional data that the filtration has to satisfy. And so that's the key observation. I mean, if X is just a trivial representation, just the 0 representation, trivial, then this is just on GLN. And so this is just saying that filtrations are just Z-weighted filtrations of a vector bundle, which is what you'd expect. And so, right. So what is the theta stratification? So basically, I can, for any stack, I can consider the following: the stack of filtered points in X is the mapping stack from theta to X, and this actually also turns out to be an algebraic stack. So I'm not giving you hypotheses or whatever, but for some very general class of stacks, this mapping stack is also algebraic. And that's just saying that, you know, this Z-weighted filter vector bundle, there's also a good meaning of what are families of Z-weighted filtered vector bundles. There's a natural definition of what are families of Z-weighted filter vector bundles once you know what it means to have a family of vector bundles. But again, on a case-by-case basis, you can unravel what this is, but just generally, this is just the answer. This is what it means to have a family of filtrations. And a theta stratification is given by an open substack. And the point is that so if the components such that the map that takes this filtration and takes a filtration to its to the underlying object is a locally closed immersion. And then there's plus some conditions that I'm not going to discuss, plus conditions on how the strata so the full definition involves an ordering of the indices of the stratification, and you know it's just, and then the closure of a stratum has to sit in the union of strata with higher index. Yeah, so basically, what this is really saying is that in the example of Harder-Narasimhan filtration, so it was the uniqueness part of the Harder-Narasimhan filtration for a bundle that says that actually the locally closed substack of vector bundles with a fixed Harder-Narasimhan filtration, you can think of that Harder-Narasimhan filtration is going to behave nicely in families. And so you can think of that as itself as a moduli problem. It's the moduli problem that parameterizes a vector bundle along with its Harder-Narasimhan filtration. And once you phrase this as a moduli problem that way, it sits inside this mapping stack, the stack parameterizing filtered vector bundles. And then the forgetful map that forgets the filtration is a locally closed immersion. So that's sort of how this is formulated. And so but the key point here is that you need to find sort of canonical maps for unstable points. And filtration now is just a map from theta to x, or in our case, MCG of x, for unstable points. Okay, so how do you actually specify this? And this is the part. So this is specified by so canonical filtrations are determined by a numerical invariant. And again, this has a meaning, but a general meaning, but I'll just say in our example, there's just a formula. So recall from up here that a filtration here is the same thing as a Z-weighted vector bundle that's compatible with some additional data associated to that vector bundle, be it an endomorphism or what have you. And the point is that for any filtration, you can assign a number. So it assigns so for any filtration, this is a number, I call this mu sub delta, that's a real number, R. And it's given by the following formula. So the formula looks like this. It looks like 1 over square root of B times L bun G plus delta Lx. And I'll explain what these terms are, what these pieces of this formula are. So L bun G is the sum over all weights of W times degree of the Wth graded piece of E minus D over R times the rank of GER W of E. So again, I'm using in our example, I'm saying a filtration is actually just a filtration as you'd expect of the underlying vector bundle with some compatibility. And so I have this Z-weighted filtration of vector bundles, and I can write down this formula. This is the degree and rank of E itself, of the underlying vector bundle itself, if you forget the filtration. So this is a numerical invariant that comes from bun G itself. It doesn't refer to the section at all. The other piece of this I'll say this is the Hilbert-Mumford weight. At the generic point of C. So basically, this is like something coming from, this comes from the GIT, this comes from the GIT parameter. This comes from GIT for X mod G itself. And the B is a quadratic form in the weights. So B is the sum of W squared times the rank of the Wth graded piece of E. So basically you have this number. It looks like it looks like a linear form in the weights divided by, that depends on delta, divided by the square root of a quadratic form in the weights. And it's actually a remarkable fact when X is just a point. It's kind of amazing that if you just look at every possible weighted filtration and you look at this real number, there's actually a unique filtration that maximizes this number, and that's the Harder-Narasimhan filtration with a particular canonical assignment of weights. So the definition is that a point is unstable if there's a map so a point, E comma S, if there's a point like that and mu of F is positive. That's the definition of stability. And then an unstable, so a Harder-Narasimhan filtration is an F that maximizes U of F subject to the constraint that F of 1 is this particular point you're looking at. So the theorem, the main theorem that I'm reporting is that this numerical invariant So Harder-Narasimhan filtrations exist, and in fact, they defines a theta stratification. And their variants with mark points and all that other kind of stuff. But yeah, so I sort of out of time. Basically, the way this theorem is proved, just to sort of illustrate why this is tricky. So for examples that are very close to abelian categories, the way that Harder-Narasimhan theorem is proved is by you take the largest subobject, a maximally destabilizing single subobject, and then the construction of the filtration is inductive. So you sort of find a maximal subobject of maximal slope, and then you look at that is forced to be semistable. You look at the quotient by that, and if that's not semistable, then you repeat this process, et cetera, and step by step you build the filtration. But in this moduli problem, the filtration has to be compatible with the additional data. So imagine that your additional data is a section of the wedge 2 of E. Then it's completely unclear. You can't really build a filtration in this moduli problem step by step, because you might have a two-term filtration. I mean, yeah, it's just not really clear how to build a filtration step by step in any meaningful way. So to prove this theorem, you need a way of showing that this function has a maximizer, which is completely different than the usual way of finding the Harder-Narasimhan filtration. In fact, it's quite difficult in general. I mean, specific examples you can do it, but in general, it's quite difficult to say what exactly is this Harder-Narasimhan filtration. So in other words, this is familiar from the world of Higgs bundles too, where the Harder-Narasimhan filtration of a Higgs bundle is some filtration of the underlying bundle that's compatible with the Higgs field, but it doesn't have to be the Harder-Narasimhan filtration of the underlying bundle. In fact, the Harder-Narasimhan filtration of the underlying bundle might not be compatible with the Higgs field. If it is, then that's still the maximizer. But so I don't know. The actual way that we prove this is by compactifying X to a projective variety, and then reducing this optimization problem to a deformation of the analogous optimization problem on Bun G itself. So so I can explain to you a little bit more about the strategy, but I just wanted to give you a little bit of a flavor of why this is a kind of a subtle thing to prove. But I'll stop there. Thank you.
Thank you very much, Dan. Great talk. Let's take some questions.
Thank you. I have two quick questions. And the first, most natural one maybe is where did this function come from that you use to define the filtration and its properties?
Yeah.
I think you called it delta.
Yeah, this function here.
Yeah.
Well, so I mean, the traditional way the traditional place where a function like this comes from is traditionally you would have you say that mu of a map like this it's the weight of some line bundle. So there's some line bundle on the stack, and you pull back the line bundle to A1 mod GM, and now it's just basically it just has a well-defined weight at the GM fixed point. And so you do say it's the weight of this line bundle divided by, and then you need some notion of a norm on F. So this is where it comes from in GIT. This is what the formula that you get in GIT, and so this is a direct, like a direct analog of that. This L bun G is the weight of a certain line bundle on Bun G. So the numerator here, this L bun G plus delta Lx, it really is an example of a weight of a certain line bundle on bun G. So it's the usual formula for Hilbert-Mumford stability. The Lx is not exactly coming from a line bundle, which is sort of strange. It doesn't come from a line bundle, but it's sort of like a line bundle at the generic point, at the generic point of C. So if you on the line bundle, if you like, on the stack of rational maps from C to X mod G.
Gotcha.
And where it comes from, so this is basically the motivation. This is the kind of formula that works out well. If you can find a line bundle or something kind of like a line bundle, that gives you the numerator of a numerical invariance. In the denominator, you need some norm on graded points. And this is all axiomatized in the general sort of machinery. But yeah, and so yeah, I didn't get into this, but there's an infinite dimensional GIT perspective that also is a guide for how to what numerical invariants are going to behave well with respect to this theory. And so yeah, so there's a sense in which the stack, you can think of it as a quotient of some analog of the Valence and Drinfeld Grassmannian. So like a big affine Grassmannian by the group of rational maps from the curve C to the group G. There's a precise way in which you can make an analogy between MCG of X kind of looks like the Valence and Drinfeld Grassmannian modulo the group of rational maps from C to G. And so basically one of the guides here is that the line bundle that you're using to define semistability should be positive on this. So the line bundles used of mu are ample on this affine Grassmannian. And it's more than actually an analogy. That this is literally the existence. The general theory reduces the existence of stratifications to two conditions, and one of the conditions is proved by making this equality precise. That there's a, yeah. The other condition is this complicated optimization problem I was telling you about. But one of the conditions is established by making sure that you start with a line bundle that's ample on this Valence and Drinfeld Grassmannian, and that makes one of the conditions work. So
I see. Thank you.
Mm-hmm.
I'm a bit scared to ask my second question now, given the technical difficulty that you just alluded to for the first question.
I'm sorry. Yeah.
But
Okay.
let me try. And then I think this infinite dimensional GIT perspective that you're saying here might be a formal way to answer it, which is in typical GIT situations that I'm familiar with, this Harder-Narasimhan-esque stratification can be generated dynamically on the analytic side by actually doing the gradient flow for the Yang-Mills functional or the Donaldson functional, or however you choose to set it up.
Yeah.
And my question would have been, insofar as you expect some analogous analytic side here, would you expect this Harder-Narasimhan-esque filtration to be generated similarly? Or is it like really just something that you have to go in there and kind of create by magic?
No, it's definitely, yeah, I would expect, yeah, it should be whatever the sort of analog of Yang-Mills flow is for the vortex equation.
Gotcha.
I mean, these moduli spaces are the moduli spaces of delta semistable objects correspond to, there's like a Kobayashi-Hitchin correspondence that they're homeomorphic to moduli spaces of solutions of the vortex equation. So you would expect a similar sort of picture. Although there's an interesting difference in the algebra geometric infinite dimensional GIT picture versus the analytic one. So in the analytic one, the spaces tend to be sort of contractible, and all of the topology is contained in the gauge group. And in this algebra geometric thing, this uniformization theorem, all the topology tends to be contained in the affine-Grassmannian, and the group of rational maps is contractible in some sense. So I've seen this in this yoga. I learned this in the papers with Gates-Gorey and some work with Gates-Gorey and Lurie. Basically, this little observation that so it's not exactly the infinite dimensional GIT picture is not exactly mapping onto the analytic picture infinite dimensional GIT, but yes, the answer to your question is yes. I would expect that the analog of Yang-Mills flow for the whatever functional gives rise to the vortex equation would correspond to these filtrations. Yeah.
Thank you. That was very helpful. Thank you.
Mm-hmm.
So Richard is asking, where is X on the right-hand side of the last equation?
Richard, can you tell me which is the last equation for you?
I think it's this.
On the right-hand side, you have the affine-Grassmannian. I was just wondering, what is the valence and does the valence and Drinfeld affine-Grassmannian that you've written there, does that involve X somehow, or where is X?
Oh yeah. Oh, I see what you mean. Yeah. So right. The X is basically you have a so this generalized valence and Drinfeld-Grassmannian. What I mean is you have a smooth family of curves, and then a divisor, and you have a G bundle on it, and it's sort of, in addition to having that G bundle, you have a section of the associated bundle on the complement of the divisor. The section of the associated bundle for X on the complement of that divisor, and now you're considering the valence and Drinfeld-Grassmannian that I'm imagining. That I'm sort of sketching for you involves considering. You start with that data, and then you consider points of the moduli stack. So a second G bundle F, and then a section of some associated bundle, and then an isomorphism away from the divisor with the data that you started with, including the section. So you want an isomorphism of so you have these two G bundles. You want an isomorphism of the restrictions away from the divisor that's compatible with the sections. And,
I see.
And that turns out to be a closed condition. So so it's really if you'd like to think of the valence and Drinfeld-Grassmannian has no X involved, then you would say that this is a closed it's a closed in subscheme of the valence and Drinfeld-Grassmannian, corresponding to isomorphisms that are compatible with this additional data of the section.
I see. And there's kind of a Drinfeld-Simpson theorem that tells you that you always have local trivializations like this. That's where the equality comes from, in other words.
Oh yeah. Yeah, I wouldn't interpret this equality to, so I wouldn't interpret this too literally. Basically what there is there's the way that this is formalized is that you have a stack like this, MCG of X, and then this maps to something like the stack of rational maps from the curve C to X mod G. And this is the stack that parameterizes this, this actually only really works for GLN. You get general G by changing the affine target. So there's some stuff that I'm sweeping under the rug, but what happens is that this is the stack that parameterizes, the stack of rational maps parameterizes a divisor in the curve, and then along with a G bundle, a G bundle and a section of the bundle, but isomorphisms are isomorphisms on the complement of the divisor. So there's a stack of rational maps that has basically the same objects, but isomorphisms in the stack are isomorphisms between those objects on the complement of a divisor. And that's no longer an algebraic stack. It's some kind of crazy thing. And then the Bailenson-Drinfeld-Grassmannian is that this sort of generalized Grassmannian is defined as a fiber product of stacks this way. So if you have a G bundle, although technically all you need is a section of the associated bundle away from the divisor, but basically you have a G bundle and a section of this associated bundle, you can regard that as a rational map, and this generalized Grassmannian is a fiber product. So there's no actual group that you're taking the quotient by, but this stack here is meant to look like this is meant to look like B. This is meant to look like the classifying stack for the group of rational maps from C to G. It's a little bit, there's still an X in that stack, so it's like it's not a perfect analogy, but the point is that you have this non-algebraic stack down here that behaves as if it's the classifying stack of a reductive group, and the fibers of this thing are in projective in schemes. And so this moduli stack here, even though it's perfectly nice algebraic stack, there's a way to think of it as something that lives over a stack that's a little bit like BG of a reductive group, and the fibers are in projective in schemes, and that's exactly what GIT is. GIT is where you study quotient stacks where X is projective. You study quotient stacks X mod G that have a map to BG, and the fibers are in projective in schemes. So this is actually how it's formalized in the paper. But I believe that if you are careful enough, you can make this equality a little bit more precise, but that's not exactly how we do it. In other words, we don't prove that this stack downstairs. Let's imagine just even when G is a point, even when X is a point, it's trivial representation. This is already a sort of interesting. Arguably interesting, but definitely like a new way to think about this moduli problem from the perspective of constructing moduli spaces and stratifications. So even when X is a point, then you just get the map, the space of the stack of rational maps from C to BG downstairs, we don't go into whether or not that's actually the classifying stack of some ind group, but morally it should be. The group of this stack map rat from C to BG is morally the classifying stack of the ind group of rational maps from C to G, if that makes sense.
Great, thanks, Daniel.
Yeah.
Okay, any more questions?
I'll go and get them. Okay, I'll be right back.
Are there any more questions? So let's thank Dan again. The next talk is going to be in 2 weeks by Konstantin Tellerman. So thank you very much. It's been great.
Thank you. Yeah, thank you very much for the invitation and for your attention.